What was that, Talon?
I thought so. This one clued me into something called the multi-tool. It's a very useful tool that, you know, is wallet size, and one of the things is the shape of a kangaroo in it. And they said if you hold it up and the kangaroo fits inside the shape, then you're far enough away. It's far enough away you can run away. If it's too big for it, too late. You can't get fat. You won't run away.
Why would you waste your time doing that?
And the temperature gauge. It's under 14,000 degrees Fahrenheit because that's the melting point of the material.
I wonder what the melting point of humans are. Or
Anyway.
kangaroos.
I found it humorous. So, any questions?
Do you know where Miram is?
I do not.
She's on her way. She
Okay.
is dropping off her brother's.
Okay. Great. David stayed to keep track of it.
I got you.
All right. It seems like we've pretty much finished 4 and 5. And I actually put down, yeah. There were some people still here when I wrote this down, but the conceptual master set due Tuesday and the application due the day after, a week from today. There are 2 master sets for 4 and 5. One of them since
As in 2 each or 2 total?
2 total.
Okay.
Which is not unusual. I just broke it down into 4 or 5 concept and 4 or 5 application. So now, let's do another slight variation. As I swing this around, if I want to hit a spot on the board, which I'm about to mark, the question ultimately is, at what point do I release it so that it hits that mark?
I would do it right when it passes your left ear.
So if I want to hit that mark,
Oh, never mind.
I'm standing here. So just for the sake of language, because I'm going to ask you to give me input here, 12 o'clock would be straight ahead, 3 o'clock, 6 o'clock, 9 o'clock, and so forth. And we will do an incredible drawing of the classroom. That's the spot. I'm going to be standing about here, swinging this thing around. So 12 o'clock, 3 o'clock, 6 o'clock, 9 o'clock. Now, if somebody says, I release it at 10:30, and the other person says 10:31, I do not have the coordination to differentiate that. So I can probably get down sort of to the nearest half hour. So at what time do I release it? Or position?
After how many revolutions?
Pardon?
After how many revolutions?
It's probably going to be about 5 revolutions, so I make sure I have control over it.
Okay. I would release it at around 7 or 8.
So around here?
Yeah.
So, yeah. All right, so 1 vote for there.
Oh,
Oh, I'm spinning it this way.
3 o'clock.
About there, yeah.
There. A little bit farther, a little bit.
A little bit closer, but
Somewhere around there,
yeah.
within a half hour.
I'm gonna say 2.
2?
Arson, my answer. I'm gonna agree with Talon.
Okay, 3 o'clock. Well, let's find out. I've done this demonstration for years.
That's not correct.
I've never hit a student doing this, just in case you were worried.
Don't make history today.
doing this with the last time I helped middle school. I was doing this. I came closer to hitting Scott than I intended. I'm still not this far away. I did not intend to be that close to him.
Do we like Scott?
Scott was an interesting person. Yeah. Overall, he was a good.
So it wouldn't have been a tragedy?
Yeah, but that was first period. And last period, somebody comes in and says, "Dr. Fox, I heard you hit Scott this morning." No, I did not hit Scott. All right, so I do need to swing it slowly enough so I have some control. So this somewhat represents it. So we'll start out with 3 o'clock. 1, 2. Sort of in that direction. My timing was off also. 2 o'clock versus 1:30. I'm just going to do some generic spot over here. So when I release it, which way does it go?
Straight.
Straight, as in, it's like this, it would go.
No, wherever you release it, it'll continue in that pattern.
Can't you do the curve?
Yeah.
Yeah. Newton's first law of motion, or second law, or pretty much second law is more precise, is that an object, if there's no force acting on an object, or the net force is 0, and acceleration will be 0, which means the velocity won't change. If the velocity doesn't change, the speed and direction are both constant. So as soon as I let go, I take a force away from the stopper, the tension disappears, and it should go in a straight line, except for the fact that there's a gravitational force, so it should move downwards.
Which it did.
Pardon?
Which it did.
Yes. But what's not going to happen is there's no memory of it's not like it's dizzy or anything like that. And when I stop spinning it, it's not going to start curving. It will go in a straight line. So that means that since it was, while I had it on the string and I was spinning it, it was not going in a straight line. Therefore, velocity was changing. Therefore, there was acceleration. And that's what we're going to explore. So far, our accelerations, at least mathematically, have always been because of a change in speed.
Can you write down what we're going to explore?
Yes.
Thank you.
Now we are going to look at acceleration because of change in direction. This is known as centripetal acceleration.
Can you remind me again what centrifugal is?
It is the opposite
Okay.
of centripetal. I'll get to that. I will say that centrifugal or centrifugal motion is usually misused. There's a proper way of using it, but people don't use it properly. So what I want to do to explore this, we have an arc of a circle, and I'm just going to assume the center is somewhere around there. Off, but hopefully close enough. So we've somewhat established that the path is tangent to the curve, or the direction that it's moving in at any point is tangent to the curve. So this is the initial. This angle right here, I'm just going to label as phi. And there's another point over here where the velocity is v final, and this angle here is phi. I'm going to establish a coordinate system here, I hat, j hat. And I want to calculate the acceleration. All right, so this formula for acceleration.
It's not mg. That's weight. Mass times. No, force equals ma. So force divided by mass.
Yeah, let's go back more toward the chapter 2 kind of definition.
Oh.
Change of velocity over change of time.
Absolutely. Nope, I was started this yet. So acceleration, change in velocity over change in time. And velocity, change in velocity, actually change in anything. How do I find change?
Initial.
Final minus initial divided. Not divided, sorry, that's the mean.
All right, so I have final velocity minus the initial velocity divided by time. So what I'm looking at, the time is the time it takes for this object that's traveling at a constant speed. So the magnitude, so VI equals VF, no vector symbol over it, indicating that the magnitudes are the same. Or I could just do that. Magnitudes are the same. I need to figure out what VF and VI are in terms of I hat and J hat. Well, if I look at sort of create a right triangle there. If this is a right angle and this angle here is phi, this angle right here must be the complement.
Can I ask a question?
Yes.
So the dotted line, the vertical one,
Yes.
those two sections at the top, is that an I or just a short dash?
That's a short dash.
Okay.
So this angle here would be the complement of phi, which I'll label as phi prime. I know that tangent to a circle is at a right angle to the radius, so that is a right angle. Therefore, this angle right here must be phi. So this angle and this angle are the same. Similar argument, this angle here is also phi. So since I have this vector VI here, a magnitude of VI, and I am breaking it into horizontal and vertical components, well, we bring our friend trig in. And so V initial is VI cosine theta I hat plus VI sine theta j hat. Pause for questions. V final is very similar to it, except the fact that it's not going up and to the right, it's going down and to the right. So it's going to be VI cosine theta I hat minus, oh sorry, VF. All these V's are the same, the magnitudes are the same, so I don't need a subscript here or here. We can do one better. Probably as close as I should get. V minus V sine theta j hat.
So VI equals VF in this case?
Yeah, speed is constant, so let's go ahead and make it official. Equals. So my acceleration is going to be my final, so V cosine theta I hat minus V sine theta j hat minus V cosine theta I hat plus V sine theta j hat divided by time. And what does that reduce? Habits are hard to break for me. There is an issue in the fact that I've labeled the angle wrong. There should be phi's, not thetas. Because I haven't defined theta at all. So that's a phi, 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 Phi is just a Greek, different Greek letter.
Does it stand for anything in this case?
The angle that I defined over there.
So it's basically theta.
Yeah.
Okay.
All right. So what does this reduce?
We need to do substitution first.
No, we need to cancel out anything that we can.
Sorry, I'm looking at my numbers. That's what I was thinking of.
Ah.
Sorry. You can cancel out the v cosines.
Yeah, because I got one there minus that.
And then there's a double negative v sine phi.
All right, so minus 2v sine phi j hat divided by time. Not particularly convenient if we actually want to use this. So we're going to put that on the side for right now. Questions before we put that to the side and do something else and come back to it? Do something else related and come back to it. Stephanie.
Is that j meant to be outside the division or on the numerator?
Is the what?
The j hat.
J hat, I could put it in the numerator or just put it off to the side, either way. By the same reason as 2x over 3 is the same as 2/3 x. Okay, now, what can you tell me about radians?
1 radian is equal to like 57 degrees.
Okay, roughly.
Isn't a radian like a proportion that is, I don't think that it has units like degrees.
It doesn't, unless you want to write rad.
Right. That's pretty much all.
So, lost it.
That's it.
That's it?
Yeah.
We're
Radians.
Oh, sorry.
Radians is equal to, degrees is divided by 180 times pi is a radian.
Okay, there's the conversion factor.
I can pull out my unit chart if that's what you're looking for.
No, I'm just curious what people know about radians. Where do we get?
They come in their exact numbers if you put them in terms of pi or square root.
At least the ones we usually deal with.
Yes, typically.
They have something to do with triangles.
Yeah, it has something to do with triangles.
And sinusoidal graphs and circles.
All right, where does 360 degrees come from? Or from where does 360 degrees come?
The right.
Who's to blame?
Somebody made it up.
Mathematicus.
Yeah, the Babylonians. We get it from them. So it's been around for a while. Babylonians had a base 60 system, and at first that might seem strange since we live in a base 10 system, but 60 actually is a very convenient number, the fact that it is divisible, at least in our language, by 1, 2, 3, 4, 5, 6, 12,
10.
sorry, thank you, 10, 12, 15, 20, 30, and 60. It's divisible by a bunch of numbers, so if there is a convenience to that. But they had special significance for the number 60. They also saw an equilateral triangle because you have equal sides, equal angles. There's something special about that. It's like a pure shape. And so if you just marry the two of them, that's 60, 60, and 60, what we now would call degrees, equilateral triangle has 60-degree angles. And if you take a bunch of equilateral triangles that are the same size, despite the way I'm drawing it, they basically sort of form a circle there in the middle. And wait, 1 too short, 1, 2, 3, 4, 5, no, that's 6. And so you got 60, 60, you got 6 60s, that's 360, that's where it comes from. That is probably one of the worst ones I've ever drawn. That's how much I care about you. I give you something special. So, especially in the 18th century, 18th, 19th century, the mathematicians said, all right, let's see if we can get math down to the purest form. Is there anything that is not man-made that we can attribute to mathematics? And they realized that if they take any circle at all, and they look at the diameter of that circle, that the ratio of how far it is around to the diameter is the same for every circle. That if you take the circumference and divide by the diameter, it's equal to some number that we now know is irrational, but that's what we label as pi. They then said, well, if we look at the radius here, half the diameter, and imagine I've got my circle here and I have my radius, and what I'm going to do is I'm going to take that length of radius and I'm just going to sort of wrap it around the edge. How far will it go? Well, the angle that is subtended here is, they said, that it seems to be natural, that it's not man-made. It seems to be true for every circle. That is 1 radian. So if the arc length is r and the radius is r, this angle here is 1 radian. And how many radii go around the entire outside of a circle?
I'm gonna assume 6 almost.
Sort of more specifically?
2 pi.
2 pi. Circumference of the circle is 2 pi r. That means you got 2 pi radii going around the outside. So there are 2 pi radians in a circle. So 2 pi radians equals 360 degrees. And if you do the math, you get 1 radian, as Robin had said, is somewhere around 57 degrees.
0.14 or something, or maybe 4.1.
I'm going to trust you on that one. I just know that when I need to